The deepest corners of space are not truly empty. They are home to enigmas that defy our most fundamental laws of physics. We are about to journey through 25 of the universe's most profound puzzles, from a hidden force pulling entire galaxies to the true nature of reality itself. By the end, you will see the cosmos in a completely new light. We will investigate why the universe's expansion is mysteriously speeding up and what a single, unexplained radio signal from the 70s might mean. Which cosmic mystery do you believe is the most important for us to solve? Our own galaxy is racing through the void at an astonishing 2 million kilometers per hour. Yet for decades, we did not know what was pulling us. The force behind this great cosmic migration is a gravitational monstrosity known as the Great Attractor. It exerts a pull so immense that it draws entire galaxy clusters, including our own Milky Way, toward a single, unseen point in the constellation of Centaurus. This is not a simple attraction. It is a fundamental reshaping of our local universe's geography, with thousands of galaxies flowing in a single, silent river. The mystery deepens because we cannot see it directly. The Great Attractor lies in a region of space astronomers call the zone of avoidance. This is not an empty void, but a place obscured by the thick dust and brilliant stars of our own galaxy's central bulge. It is as if the universe placed its most powerful secret behind a brilliant, blinding curtain. For a long time, this region was a complete blank spot on our cosmic maps, a frustrating blind spot hiding an answer to one of our biggest questions. How do you study something you cannot see? You look with different eyes. Modern telescopes, like those that observe in infrared and X-ray wavelengths, are finally peeling back the cosmic dust. They can see through the obscuring material of our galaxy, revealing the structures hidden in the zone of avoidance. What they have found is not one single, colossal object, but an unbelievable concentration of mass, a vast supercluster of galaxies known as the Norma Cluster. This dense knot of galaxies and the immense amount of dark matter associated with them is the primary source of the gravitational pull. Even so, the story does not end there. The Great Attractor itself is being pulled. The entire flow of galaxies in our region, including the attractor, is being drawn toward an even larger and more distant structure, a colossus known as the Shapley supercluster. This reveals a cosmic hierarchy of gravity, a tug of war on a scale that is almost impossible to comprehend. Where our local universe is caught in a web of pulls and counterpulls from concentrations of mass we are only beginning to map. This invisible force holding galaxies together points to an even greater enigma, a ghost in the cosmic machinery known as dark matter. We can map its gravitational grip with incredible precision, knowing it constitutes over a quarter of everything in the universe, yet we have never directly seen a single particle of it. The first compelling clue emerged from the way galaxies spin. According to the laws of gravity, stars on the outer edges of a spinning galaxy should move much more slowly than those near the bright center, just as Pluto orbits our sun far more sluggishly than Mercury. But observations tell a very different story. Stars at the distant edges of spiral galaxies whirl around at speeds just as fast as those closer in. It is as if the entire galaxy is embedded within a vast, invisible sphere of mass, a halo of something that we cannot see, whose gravity is the only thing preventing these far-flung stars from flying off into the void. This something is dark matter. Another line of evidence comes from gravity's own trick with light, a phenomenon called gravitational lensing. Einstein showed that massive objects warp the fabric of space-time, bending the path of light that travels near them. When astronomers look at massive galaxy clusters, they sometimes see distant galaxies behind them stretched and distorted into faint, shimmering arcs. The amount of bending is often far greater than the visible mass of the cluster can account for. There must be an enormous amount of unseen mass, dark matter, creating a deeper gravitational well that twists the light like a cosmic magnifying glass. So what could this mysterious substance be? It is not made of atoms, the building blocks of everything we see. It does not interact with light at all, which is why it is completely transparent and dark. The leading candidates are exotic particles that barely interact with normal matter. One hypothetical particle is called a WIMP, which stands for weakly interacting massive particle. These would be heavy particles that only feel gravity and the weak nuclear force, passing through our planet and our bodies by the trillions every second without a trace. Another candidate is the action, a particle that is fantastically light, but could exist in such overwhelming numbers that it accounts for all the missing mass. Picture our galaxy not just as a disk of stars, but as a glowing pearl suspended within a giant, diffuse cloud of these elusive particles, a cloud whose gravity dictates the very motion of every star we see. The true nature of dark matter remains one of physics' most profound puzzles, an invisible architecture holding the visible universe together. While dark matter's gravity pulls the cosmos together, a far more mysterious force is actively pushing it apart. The discovery that the universe's expansion is not slowing down, but accelerating, completely overturned our understanding of cosmic destiny. This revelation came from studying the most powerful stellar explosions in the universe, supernova. Astronomers used these brilliant beacons to measure vast cosmic distances, expecting to find that the expansion from the Big Bang was gradually decelerating over time, pulled back by the collective gravity of all matter. Instead, they found the opposite. The most distant supernova were fainter than they should have been, meaning they were farther away than anyone predicted. The universe's expansion is speeding up, as if some unseen repulsive force is stretching the very fabric of space. This monumental discovery earned the lead researchers the Nobel Prize in Physics in 2011, cementing one of the most unsettling truths in modern cosmology. The mysterious culprit was given a name, dark energy. So what is this force that counteracts gravity itself? One of the oldest candidates comes directly from Einstein's equations. He originally introduced a fudge factor called the cosmological constant to keep the universe static, a concept he later called his greatest blunder. Yet it seems he may have been right for the wrong reason. The cosmological constant represents a constant energy density inherent to the vacuum of space itself. Think of empty space not as truly empty, but as a seething foam of virtual particles popping in and out of existence. This quantum jitter could generate a gentle, pervasive pressure that pushes space apart. The problem is, when physicists calculate the predicted strength of this vacuum energy, the result is wrong by a factor of 1 followed by 120 zeros. It is the most severe discrepancy between theory and observation in the entire history of science. This colossal failure has led to other, even stranger ideas. Perhaps dark energy is not a constant force at all, but a dynamic field that changes over time, dubbed quintessence. Or maybe our understanding of gravity itself is fundamentally flawed on the largest scales, and Einstein's theory of general relativity needs a revision. The fate of the entire cosmos hinges on the true nature of this mystery. If dark energy remains constant or grows stronger, the acceleration will continue forever, leading to a cold, lonely end where distant galaxies eventually fade from view, leaving an isolated and dark universe. This invisible force, making up about 70% of the universe, is the dominant player in our cosmic story, yet we have no idea what it actually is. The accelerating expansion of the cosmos presents a lonely future, but the silence we hear today is even more profound. With billions of potentially habitable planets in our galaxy alone, the universe should be teeming with life. So where is everybody? This is the core of the Fermi Paradox, a simple question with terrifying implications. The physicist Enrico Fermi first posed it over lunch in 1950, looking up at the sky and essentially asking why, if the numbers are so favorable, we see no signs of engineers. The contradiction is staggering. We have discovered thousands of exoplanets, many within the habitable zones of their stars, where conditions could be right for life as we know it. Given the age of the universe, there has been more than enough time for intelligent civilizations to arise, develop technology far beyond our own, and spread across the galaxy. Their presence, in theory, should be unmistakable. We should see the glow of their city lights on distant worlds, hear the chatter of their communications, or find the ghostly outlines of vast engineering projects. Instead, we are met with an immense and unbroken silence. The stars shine down on a cosmos that appears, for all intents and purposes, empty. This great silence forces us to confront some unsettling possibilities. One of the most daunting is the concept of the Great Filter. This theory suggests that there is some kind of barrier, a single, incredibly difficult step in the evolution of life that prevents civilizations from reaching the stars. The filter could lie in our past. Perhaps the jump from simple prokaryotic cells to complex eukaryotic life is a rare fluke, a 1 in a trillion event. If that is the case, then we are already past the filter, and we might truly be alone. The more frightening prospect is that the filter lies in our future. Maybe there is some inevitable cataclysm that awaits all technological species, a self-destruction through war or a runaway technology that we have not yet encountered. In this scenario, the silence is the sound of countless civilizations that have already risen and fallen. Other solutions are less grim but equally mind-bending. The zoo hypothesis proposes that advanced civilizations are aware of us, but have chosen to place us in a kind of cosmic quarantine, observing from a distance to allow our natural development without interference. Alternatively, their nature or technology might be so fundamentally different from our own that we simply lack the means to perceive them. Their communications might not use radio waves, but something we cannot yet detect, like neutrino beams or manipulations of space-time itself. Perhaps they have transcended physical form, existing as digital consciousness within vast computer networks, leaving the material universe behind. We might even be looking for the wrong signs, missing the subtle evidence of astroengineering on a staggering scale. Imagine a civilization so advanced it builds a Dyson sphere, a hypothetical structure that encircles a star to capture nearly all of its energy output. To us, that star would simply vanish from the visible spectrum, replaced by a weird, warm glow of infrared light. We have actually found a few candidate stars that behave in this bizarre way, though natural explanations are more likely. The truth is, the silence is not an answer, but a mirror. It reflects our own ignorance and forces us to question everything we think we know about life, intelligence, and our own future. That profound silence was broken, if only for a moment, on a warm August evening in 1977. An astronomer named Jerry Amon was volunteering for the SETI project, carefully reviewing reams of data from the Big Ear radio telescope at Ohio State University. As his eyes scanned a computer printout, he saw a sequence of letters and numbers that made him freeze. The signal was so powerful and so perfectly structured that he grabbed a red pen and circled it, writing a single, emphatic word in the margin, "Wow." This was not random cosmic noise. The wow signal was a strong, narrowband radio burst, precisely at the frequency of 21 centimeters, the wavelength emitted by neutral hydrogen. Hydrogen is the most common element in the universe, and many scientists had theorized that an advanced civilization might use this universal channel as a logical beacon. The signal lasted for 72 seconds, the exact duration the Big Ear telescope could hold a fixed point in the sky, and it came from the direction of the constellation Sagittarius. It rose and fell in intensity in a perfect curve, just as you would expect from a celestial source passing through the telescope's field of view. It was, by all accounts, the perfect candidate for a message from the stars. The hunt was on. For decades, astronomers have pointed their most powerful radio dishes toward that same patch of sky, listening intently for a repeat performance. They have scanned the same frequency, hoping to catch another whisper from the void. The result has been a resounding and puzzling silence. Nothing like the wow signal has ever been detected again. This enduring mystery has fueled a long and unresolved debate. Was it a human-made signal reflected off a piece of space debris? This seems unlikely, as the frequency was protected, reserved for astronomical research, and not used by earthly transmitters. Could it have been a natural astrophysical event, a previously unknown type of stellar flare, or a quasar's outburst? No known natural phenomenon produces such a focused, narrowband radio burst. In 2016, a team proposed a controversial solution, suggesting the signal came from a comet that happened to be passing through that region of space. Comets are surrounded by large clouds of hydrogen gas, which could theoretically emit a strong signal. The timing and location seem to align with two known comets. But this explanation has been largely dismantled. The comets were not actually in the telescope's field of view at that precise moment, and the specific frequency and signature of the wow signal do not match the broad emissions from a comet's hydrogen cloud. So we are left with a ghost, a signal that appeared once with stunning clarity and then vanished forever. It stands as a tantalizing, solitary data point in our search for cosmic company, a single, perfect note played in an otherwise silent concert hall. It proves that the cosmos is capable of producing signals that look exactly like the ones we are searching for, yet it refuses to give up its secret. The wow signal remains a singular, unexplained event, but the cosmos holds other silences even more vast and structural. Far beyond any local quiet, there exists a region of space so profoundly empty it defies our basic understanding of the universe's structure. This is the Boötes Void, a spherical chasm of near-nothingness spanning an almost unimaginable 330 million light-years. If you placed our Milky Way at its center, you would have to travel for 150 million years at the speed of light in any direction before you would even have a chance of reaching another galaxy. This is not merely a sparse neighborhood. It is a true cosmic desert, one of the largest voids ever discovered. Its existence challenges everything we know about how matter is distributed across the cosmos. On the largest scales, the universe resembles a vast cosmic web, an intricate lattice of brilliant galaxy filaments and clusters surrounding these dark, empty voids. The Boötes Void is one of the largest holes in that web. So how does such an immense nothingness come to be? One leading theory points back to the very first moments of the universe, to a period of faster-than-light expansion called cosmic inflation. During this initial violent stretching, tiny quantum fluctuations were magnified to astronomical sizes. These ripples in the fabric of reality became the blueprints for all future structure. The denser regions eventually collapsed under gravity to form galaxy clusters and the great filaments we see today. The underdense regions, however, kept expanding, their matter draining away toward the denser walls like water flowing from a bathtub. The Boötes Void could be one of these primordial underdense regions, a bubble that was mostly empty from the very beginning and just kept growing. Another possibility is that the void is not entirely empty, but is shaped by structures even larger than we can easily perceive. The gravitational pull from an incredibly massive supercluster just beyond the void could have acted like a cosmic vacuum cleaner, slowly pulling galaxies out of the region over billions of years, leaving behind the desolate expanse we observe today. What does this colossal emptiness tell us? It reveals that the universe is far more lumpy and textured than we ever imagined. It is not a uniform soup of galaxies, but a tapestry of rich clusters and staggering deserts. The void itself is not completely barren, however. Painstaking surveys have located a handful of galaxies drifting in this immense darkness, isolated islands, in a sea of nothing. These lonely galaxies are crucial for astronomers as they act as probes. By studying how their light is subtly reddened by the ongoing expansion of the universe, scientists can map the void's gravitational field and measure its true mass, including the contribution of dark matter that must still be woven throughout the emptiness. The Boötes Void forces us to confront the sheer scale of cosmic structure and the powerful, sculpting force of gravity acting over billions of years. It is a reminder that the grandest patterns in the universe are written not only in the brilliant cities of stars, but also in the vast, silent spaces between them. The pristine afterglow of the Big Bang should be a uniform tapestry, but it holds strange, ghostly imprints that refuse to fit our models. This is the cosmic microwave background radiation, the oldest light in the universe, released when the first atoms formed and space became transparent. It is a snapshot of the infant cosmos, a faint, cold glow that fills all of space. For decades, the standard model of cosmology held that this background should be almost perfectly smooth, with tiny, random fluctuations seeded by quantum ripples in the universe's first moments. But when satellites like WMAP and Planck mapped this glow with incredible precision, they found bizarre anomalies, cosmic wrinkles that should not be there. One of the most famous is the cold spot, a vast, unusually cool region in the southern sky that spans nearly 1 billion light years. It is far larger and colder than our theories can easily explain. It is as if a giant cosmic void has been stamped on the fabric of the universe, a place where there is significantly less matter, and therefore less energy than anywhere else. But the scale of such a void would be unprecedented, challenging our understanding of how structure forms. Another, even more unsettling anomaly is what some scientists have dramatically nicknamed the axis of evil. This is not a single feature, but a strange alignment in the patterns of the CMB. The fluctuations appear to be oriented along a particular axis in space, a preferred direction that breaks a fundamental rule of cosmology, the principle that the universe should look the same in all directions. It suggests a cosmic tilt, a lopsidedness to the entire universe that makes no sense within our standard framework. How could the universe have a preferred axis? The explanations scientists have proposed are as radical as the anomalies themselves. For the cold spot, one breathtaking theory suggests it could be the bruise from a collision with another universe. In a multiverse scenario, our cosmos might have bumped into a neighboring bubble universe in the distant past, and the energy of that collision left a cold imprint on our sky. Other, less exotic ideas posit that it is just a statistical fluke, a 1 in 100 chance that we happen to see in our particular patch of the cosmos. The axis of evil is even harder to explain away. It could mean our standard model of the Big Bang is incomplete, missing a key piece of physics that imprinted a direction onto the cosmos at birth. Or more simply, it could be contamination from our own cosmic backyard, the gravitational influence of the nearby Shapley supercluster tugging on the light and creating an illusion of alignment. Yet, when astronomers correct for these local effects, the signal stubbornly remains. These cosmic ghosts in the machine force us to question the very foundations of our cosmology. Is the universe truly isotropic and homogeneous, as we have long assumed, or is it subtly textured with features that hint at a far grander and more complex reality? The all-sky maps from Planck are not just pictures of our origin. They are cryptic messages from the dawn of time, and we are only just beginning to decipher their deepest secrets. While we map the grandest structures in the cosmos, some of the most stubborn mysteries are found much closer to home, in the silent journeys of our own robotic explorers. For decades, two intrepid spacecraft, Pioneer 10 and Pioneer 11, sent back a steady stream of data as they sped toward the outer planets and beyond. But as they journeyed farther from the sun, a tiny, persistent ghost appeared in the numbers. Both probes were experiencing a constant, unexplained deceleration, a slight but undeniable pullback toward the inner solar system. This was the Pioneer anomaly, a minuscule drift that defied all predictions. It was as if an invisible hand was gently applying the brakes, a force equivalent to just 10 billion times weaker than the gravity we feel on Earth, but it was there, and it refused to go away. For years, this tiny signal haunted physicists. Was it a flaw in our understanding of gravity itself? Did Newton's laws, so reliable for centuries, break down at the vast distances of interstellar space? Perhaps it was evidence of some unknown, diffuse matter scattered throughout the solar system, or even a hint of dark matter's local influence. The tiny deceleration became a monumental puzzle. The solution, when it finally came, was not from the realm of exotic physics, but from simple, practical engineering. Every spacecraft generates heat from its radioactive power source, and that heat must radiate away. Scientists realized that the Pioneer probes were not perfectly uniform. One side of the craft, with its main antennae pointed steadily back at Earth, radiated slightly more heat than the other sides. This created a tiny but constant recoil force. It was the gentle, unseen push of photons, the particles of light and heat, streaming off the warm spacecraft. Just as a garden hose kicks back when you turn on the water, this anisotropic thermal radiation was pushing back on the Pioneers, creating the illusion of a mysterious deceleration. The case was considered largely closed, a triumph of meticulous analysis over cosmic mystery, yet a whisper of doubt remains. When researchers meticulously modeled all the thermal effects, they found it accounted for most of the anomaly, but perhaps not all of it. A tiny fraction of the original signal, a residual drift, seemed to linger. Was this just the limit of our modeling precision, the inevitable noise in a decades-old dataset? Or could it be a sign that something else, something still unknown, was subtly acting on those lonely spacecraft as they sailed into the black? The Pioneer probes are now silent, their power long since faded, but the lesson of their journey endures. Sometimes the universe's greatest secrets are not written in the light of distant quasars, but hidden in the faint, stubborn signal from a machine we built ourselves. A reminder that the cosmos still holds surprises in the smallest of details. That faint, stubborn drift from our Pioneer probes is a whisper compared to a cosmic scream that echoes across the universe. Without warning, a point in the sky erupts, releasing more energy in a single millisecond than our sun puts out in 3 days. Then, just as suddenly, it is gone. These are fast radio bursts, or FRB, and they are one of the most explosive puzzles in modern astronomy. The first one was discovered in 2007, hidden in archival data from the Parkes Radio Telescope in Australia. It was so brief and so powerful that for years, many astronomers dismissed it as a glitch, perhaps a malfunctioning microwave oven on the observatory grounds. But then more were found, proving these were genuine cosmic events. Their defining feature is their incredible brevity. An FRB is a flash of radio light that blinks into existence and vanishes in the time it takes a camera shutter to click, a burst of pure energy from the deepest voids between galaxies. The mystery intensified when astronomers realized these bursts were not all the same. Most are one-off events, a single, spectacular flash from a source that never repeats. But a few are repeaters, firing off multiple bursts from the same location in the sky, sometimes in a frantic, unpredictable pattern, other times in a steady, almost predictable rhythm. This crucial distinction between one-off and repeating FRBs immediately suggested there might be at least 2 different kinds of cosmic engines powering these phenomenal explosions. So what celestial object can produce such a staggering release of energy in an instant? For the one-off bursts, the leading suspects are cataclysmic events, the final, violent acts of cosmic objects. Imagine 2 ultra-dense neutron stars, each the crushed core of a dead star, locked in a final, spiraling dance. Their merger would create a gravitational shockwave of immense power, potentially capable of launching a one-time colossal radio burst. Another possibility is the death of a special kind of star, a magnetar. These are neutron stars with magnetic fields so intense they could erase a credit card from half the distance to the moon. A starquake on the surface of a magnetar, a sudden cracking of its rigid crust, could unleash a flare of energy that we see as a fast radio burst. This theory gained significant support when, in 2020, a magnetar within our own galaxy erupted with a burst that, while weaker, had all the hallmarks of an FRB. For the repeating bursts, however, the cataclysm theory falls apart. An object cannot be destroyed more than once. This points to a source that can survive its own outburst, something that can fire again and again. A highly magnetized neutron star, like a magnetar, could potentially produce repeated flares if it is in a particularly active and unstable state, its crust constantly shifting under unimaginable magnetic stress. The sheer power and bizarre nature of these signals have inevitably led to more speculative ideas. Could some of them, particularly the highly organized repeating bursts, be artificial in origin? Perhaps they are the leakage from incredibly powerful transmitters on alien spacecraft, or beacons from an advanced civilization. While this is the least likely explanation, it highlights just how extraordinary these events are. They push the limits of known physics, forcing us to consider every possibility. These millisecond flashes are more than just cosmic fireworks. As their radio waves travel billions of light years to reach us, They pass through the diffuse clouds of gas and dust that drift in the space between galaxies. This material subtly distorts the signal, and by reading that distortion, astronomers can use FRBs as cosmic probes to weigh the missing matter in the universe, the ordinary atoms that have been hiding in plain sight. Each burst is a brief, brilliant flare illuminating the shadowy structure of the cosmic web itself. But these cosmic flashes are not the only evidence that our place in the universe might be special and strangely empty. A growing body of evidence suggests we are living inside a vast cosmic void, a billion light-year wide bubble of relative nothingness known as the Boötes Void, named for the scientists who first proposed it. This is not a complete emptiness like the Boötes Void, but a region where the density of galaxies, clusters, and even dark matter is significantly lower than the cosmic average. Imagine the universe as a sprawling metropolis. Most observers live in the bright, crowded downtown districts, surrounded by skyscrapers and bustling streets. We, however, seem to be residing in a quiet, sparsely populated suburb on the far outskirts. The evidence for this comes from several independent lines of inquiry. When astronomers perform detailed galaxy counts in all directions around us, they find fewer neighbors than standard models predict. The local universe seems a bit too spacious. Furthermore, measurements of distant supernovae, the same ones used to discover dark energy, appear slightly brighter than they should if space were uniformly filled. In an underdense void, the fabric of space itself expands a little faster locally because there is less gravitational pull from matter to slow it down. This means light from a supernova traveling through our local bubble has a slightly easier journey, making it appear brighter to our telescopes, as if the cosmic distance ladder has a rung slightly out of place. The most profound implication of this local void hypothesis involves one of the biggest conflicts in modern cosmology, the Hubble constant. This number describes how fast the universe is expanding today. There are two primary ways to measure it. One method uses the cosmic microwave background, the afterglow of the Big Bang, to predict the current expansion rate. The other directly measures the speeds and distances of nearby stars and supernovae. These two methods, each incredibly precise, have stubbornly refused to agree. The local measurements consistently give a faster expansion rate than the one predicted from the early universe. If we are indeed inside a giant void, this discrepancy could be explained. The lower density in our local bubble would allow space to expand faster here than in the denser, average universe. Our local measurements would be capturing this boosted, outlying expansion rate, while the cosmic microwave background reflects the true, slower average for the cosmos as a whole. Our unique, secluded address would be skewing our perception of the entire universe's expansion. Not all astronomers are convinced, however. The debate is fierce. Critics argue that a void as large as the one proposed would be incredibly rare, a statistical anomaly in our standard model of cosmology. They suggest that unknown errors in our distance measurements or complexities in how supernovae explode are more likely culprits for the Hubble tension. The existence of the Boötes Void remains a compelling but controversial hypothesis. It forces us to confront a humbling possibility that our entire cosmic neighborhood might be an underdense backwater, and that our view of the universe is fundamentally biased by our quiet location in the grand cosmic web. This strange cosmic tilt, nicknamed the axis of evil, is not a malevolent force but a statistical nightmare for cosmologists. It refers to a bizarre alignment in the oldest light we can see, where the hot and cold spots in the cosmic microwave background appear to be subtly coordinated with the plane of our own solar system. This is deeply unsettling because it suggests a preferred direction in the universe, a fundamental lopsidedness that contradicts the cosmological principle, the foundational idea that the universe is homogeneous and isotropic, meaning it should look the same in all directions and have no center or edge. Finding a correlation with our own local space feels like discovering that the grandest tapestry in creation is subtly aligned with the floorboards of your own house. The chance of this happening randomly is incredibly small, less than 1 in 1,000. This has forced scientists to ask a haunting question: is the signal real, or is it a ghost in our machine? The first and most conservative explanation is some form of systematic error, an unknown contamination from our own cosmic backyard. Perhaps the gravitational pull of the nearby Virgo supercluster is subtly distorting the CMB light as it passes through, creating an illusion of alignment. Or maybe there is an unaccounted-for foreground emission within our own galaxy, a faint haze of dust or energetic electrons that the Planck satellite's sensitive instruments mistook for the primordial background. Researchers have meticulously subtracted these known local influences, yet the strange alignment stubbornly persists in the cleaned maps. If the axis of evil is a real feature of the primordial universe, its implications are staggering. It could mean that the universe is not the same in all directions on its largest scales, that there is a fundamental grain to reality, much like the grain in a piece of wood. This would force a complete rewrite of our standard model of cosmology. Some theorists have proposed that this preferred direction could be a fossil from a time before the Big Bang, an imprint from a previous cosmic phase, or a collision with another universe that set a spin or a tilt to our entire cosmos. Others suggest it points to a pre-existing structure, a relic of a more profound quantum gravity realm that seeded our universe with an inherent asymmetry. The most powerful tool for investigating this mystery lies in the subtle polarization of the CMB light, a specific directionality imprinted on the photons. If the axis of evil is a real cosmological feature and not a local fluke, its signature should also be stamped into this polarization data. The latest, most detailed polarization maps from the Planck mission have been scrutinized for this very signal. The results are, for now, inconclusive. Some analyses claim to see a faint echo of the alignment, while others find no compelling evidence. This leaves us in a state of profound uncertainty, standing before a cosmic clue that could either be the key to a deeper reality or the most elaborate statistical illusion in the history of science. This missing matter is not the elusive dark stuff, but the ordinary atoms that make up everything we can see, from stars to our own bodies. Based on the pristine conditions of the Big Bang, we can calculate with remarkable precision how much of this normal matter, also called baryonic matter, should exist in the universe today. Yet when we add up all the stars, galaxies, and visible gas clouds, we come up drastically short. Nearly half of all the atoms that should be there are simply missing from our cosmic inventory. So where did they go? The leading suspect is not a place, but a state. Scientists believe the missing matter is hiding in a diffuse, superheated fog known as the warm-hot intergalactic medium, or WIM. This is not a cloud you could see or fly through, but a tenuous web of gas filaments stretched between galaxies, heated to temperatures of hundreds of thousands, even millions of degrees. At such extreme heat, the gas is ionized, meaning its atoms are stripped of their electrons, making it completely invisible to optical telescopes. It is the universe's most effective hiding place, a ghostly ocean of matter that has, until now, escaped our notice. This warm, hot intergalactic medium is woven directly into the architecture of the cosmic web. Picture the universe's large-scale structure not as isolated galaxies, but as a vast sponge. The dense knots where the filaments intersect are the great galaxy clusters, but the strands of the sponge itself, the long, thin filaments that connect everything, are where the whim is thought to reside. Gravity slowly pulls ordinary matter along these invisible highways, feeding the clusters and superheating the gas in the process. Finding this gas is a detective story of cosmic proportions. Since it is too hot to glow in visible light, astronomers must use indirect methods. One powerful technique involves using distant beacons known as quasars. These are incredibly bright galactic cores, and their light travels for billions of years to reach us. As this light passes through the filaments of the cosmic web, the ionized gas in the WIM absorbs specific, very high energy wavelengths like X-rays. By analyzing the quasar spectrum, scientists can see the faint, dark absorption lines where the light has been subtracted, revealing the chemical fingerprint and location of the invisible WIM. It is like identifying a distant forest by the specific shadow it casts on a brilliant backdrop. New generations of space telescopes, like ESA's XMM Newton and NASA Chandra X-ray Observatory, are now sophisticated enough to perform this delicate analysis. Furthermore, the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background caused by hot gas scattering the ancient light, provides another way to weigh this diffuse material. Supercomputer simulations of the universe's evolution show this exact scenario, predicting a vast, intricate network of hot gas filaments where the missing baryons should be pooled. The hunt is finally yielding results. In recent years, astronomers have announced the first definitive detections of the WIM, identifying these vast, hot filaments by carefully correlating the positions of distant quasars with the predicted structure of the cosmic web. They are slowly mapping the unseen architecture of the universe, filling in the blank spaces on the cosmic ledger. This discovery closes a major chapter in cosmology, confirming that the atoms we have long been searching for were not truly missing, but merely hiding in plain sight, woven into the very fabric of the cosmos. The universe should be raining down death from above. Cosmic rays, atomic nuclei accelerated to nearly the speed of light, constantly bombard our atmosphere. Most are low-energy particles, but a tiny fraction carry energies so immense they defy belief, packing the kinetic energy of a professionally thrown baseball into a single subatomic particle. According to a prediction made over 50 years ago, such particles should not be able to reach us from distant galaxies. This is the GZK cutoff, a theoretical limit named for the physicists Greisen, Zatsepin, and Kuzmin. Their calculations showed that any proton with an energy above a certain staggering threshold would be doomed as it traveled through space. It would inevitably collide with a photon from the cosmic microwave background, the cold relic of the Big Bang that fills all of space. That seemingly gentle collision at such incredible speeds would be catastrophic. It would rip the proton apart, creating a shower of less energetic particles and effectively erasing the ultra-high-energy cosmic ray from existence. The universe, it seemed, had a built-in speed limit for these atomic bullets, preventing them from crossing vast intergalactic distances. Our corner of the cosmos should be a quiet, safe zone, shielded from the most powerful particle accelerators in the universe. Then we started looking. Giant observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah are designed to detect these rare events. They do not catch the particle itself, but the enormous cascade of secondary particles it creates when it strikes the top of the atmosphere, a sprawling umbrella of decay that can cover dozens of square miles. To the complete astonishment of physicists, these detectors have recorded multiple cosmic rays with energies far beyond the Gizike cutoff. These are the ultra-high-energy cosmic rays, and their very existence is a profound violation of our expectations. They are here, which means our understanding of their journey is fundamentally wrong. How did they survive the trip? One compelling idea is that they did not have a long journey at all. Perhaps these particles are not coming from billions of light years away, but from somewhere relatively close within our local supercluster of galaxies. If their source is within about 150 million light years, they would not have had enough time to be destroyed by the microwave background radiation. The problem is, when astronomers trace the rough paths of these particles back into the sky, they do not point to any obvious cataclysmic source. There are no nearby active galaxies or brilliant gamma-ray bursts in the right directions. The sources remain ghostly and unidentified. This has led to more radical proposals. Could this be a sign of new physics? Perhaps the Lorentz invariance, a cornerstone of Einstein's special relativity that dictates how particles gain mass as they approach light speed, breaks down at these extreme energies. If that were true, the rules of the game would change, and these protons could potentially avoid the destructive collisions that the Gizike prediction relies upon. Or maybe these are not protons at all, but much heavier atomic nuclei like iron. Heavier nuclei have a different interaction threshold with the background radiation, which could potentially allow them to travel farther without being completely destroyed. Yet another possibility is that our measurements are flawed, that the complex process of reconstructing the energy of these air showers from the ground has a systematic error we do not yet understand. But with multiple independent observatories seeing the same phenomenon, this seems less likely. Each of these cosmic bullets that strikes our atmosphere is a messenger from the most violent processes in the universe, a challenge to our models written in the language of raw energy. Their unexplained arrival forces us to question the laws of physics themselves and wonder what unimaginable engines, hidden in the void, are capable of hurling matter across the universe with such ferocious power. This growing disagreement over the universe's expansion rate is more than a minor calibration error. It is a full-blown crisis in cosmology known as the Hubble tension. On one side, we have the view from the beginning. The Planck satellite mapped the cosmic microwave background with exquisite detail, and by analyzing the subtle patterns in this baby picture of the universe, scientists can predict how fast the cosmos should be expanding today. This method gives us one very precise number. On the other side, we have the view from our own cosmic neighborhood. Astronomers use celestial yardsticks like Cepheid variable stars, whose predictable pulsations reveal their true brightness, and Type Ia supernova, the standard candles that revealed dark energy. By measuring how fast these objects are rushing away from us, we get a direct, local measurement of the expansion rate. This method gives us another, equally precise number. The problem is, these two numbers disagree. The local measurements consistently show a universe expanding about 10% faster than the early universe data predicts. Imagine two incredibly accurate clocks, one built from the universe's first moments and the other from stars in our backyard, and they are ticking at undeniably different rates. This is not just a statistical fluke. The gap has only widened with better data, pushing the discrepancy to a confidence level of 5 sigma, a threshold in physics that typically signals a real discovery, not an error. This tension points to a potential crack in our standard model of cosmology. Perhaps we are missing an ingredient that was active in the early universe. One compelling candidate is early dark energy, a speculative form of energy that could have briefly surged during the first few 100,000 years after the Big Bang. This extra push would have subtly altered the conditions imprinted on the cosmic microwave background, leading to a different prediction for today's expansion rate and potentially reconciling the two values. Other ideas involve tweaking the universe's contents, such as proposing the existence of sterile neutrinos, hypothetical particles that interact only through gravity and could change how structures formed in the primordial cosmos. The most radical possibility is that our understanding of gravity or the nature of dark energy itself is flawed in a way that manifests differently across cosmic time. Teams are now deploying every tool at their disposal to resolve this conflict. The James Webb Space Telescope is now scrutinizing the same Cepheid stars and supernovae used for the local measurement, checking for any hidden systematic errors with its pristine infrared vision. Meanwhile, new observatories are looking for entirely independent ways to measure the expansion, such as using the gravitational waves from colliding neutron stars as standard sirens. The Hubble tension is not a failure of science, but a thrilling signal. It is the universe telling us that our map of reality is incomplete, and that the next great breakthrough in understanding may be hidden within this stubborn, persistent disagreement. That profound silence has not gone unchallenged. For over 6 decades, scientists have been actively scanning the heavens, using enormous radio telescopes like the one in Arecibo to listen for a whisper of artificiality in the cosmic static. This is the search for extraterrestrial intelligence, or SETI, a grand experiment fueled by one simple question: is anyone out there? The technical challenges, however, are almost beyond comprehension. The universe is incredibly loud, filled with the natural radio chatter of pulsars, quasars, and interstellar gas. Picking an intelligent signal out of that noise is like trying to hear a single, specific conversation in a stadium packed with roaring fans. And then there is the sheer vastness of space to consider. Our most powerful broadcasts, like early television transmissions, have only traveled about 100 light years from Earth, a mere bubble in the ocean of the Milky Way. A civilization would need to be pointing a receiver directly at us, at exactly the right time, and listening on the correct frequency to even have a chance of noticing we are here. The more we learn, the more we are forced to consider that intelligence might not look anything like us. A civilization just a few thousand years more advanced than our own could have transcended biology entirely, evolving into forms we might not even recognize as life. Imagine a species that has uploaded its collective consciousness into a planetary-scale computer network, existing as pure information in a climate-controlled server farm the size of a continent. Or perhaps they have engineered themselves into microscopic nanites, spreading through the galaxy like a dust cloud. Such post-biological beings would have no need for the radio signals we are searching for. Their conversations might take place through quantum entanglement or through manipulations of spacetime itself, methods completely invisible to our current technology. This leads to a deeply controversial offshoot of the search, known as active SETI or METI, which stands for Messaging Extraterrestrial Intelligence. Instead of just listening, this involves deliberately broadcasting powerful, targeted messages to nearby star systems. The idea is to jumpstart the conversation, to announce our presence to the cosmos. But many prominent scientists, including the late Stephen Hawking, have warned against this. They compare it to shouting into a dark and unknown forest. If history is any guide, he argued, meetings between advanced and primitive civilizations have rarely ended well for the less advanced one. The ethical implications are staggering. Should a handful of people on one planet have the right to speak for all of humanity and potentially attract attention we cannot handle? The silence, then, might not be empty. It could be a choice, a universal precaution taken by intelligent species who have learned that the cosmos is safest when you stay quiet. Or it could be a sign that we are simply too young, too primitive, to understand the language in which the universe truly speaks. Deep within a black hole's crushing darkness lies a point where physics itself comes to an end. This is the singularity, a place of infinite density where the known laws of the universe, Einstein's elegant theory of general relativity, simply shatter. According to the math, all the matter that ever fell into the black hole is crushed into a point with zero volume, where gravity becomes infinite and space and time cease to have any meaningful definition. It is a cosmic dead end for mathematics, a sign that our current understanding is profoundly incomplete. This breakdown forces us to seek a deeper theory, one that can marry the vast cosmic scale of gravity with the bizarre, probabilistic rules of the quantum world. This unified theory of quantum gravity would reveal the true nature of the singularity, not as an infinite point, but as something else entirely, a structure governed by the foaming, frenetic energy of the quantum realm. Imagine the fabric of space-time at this scale not as a smooth sheet, but as a bubbling chaos of virtual particles, a quantum foam where tiny wormholes constantly blink in and out of existence. This is the theoretical landscape where answers might be found. Two leading candidates, string theory and loop quantum gravity, offer very different visions of this heart of darkness. String theory proposes that the fundamental building blocks of the universe are not point particles, but incredibly tiny, vibrating strings. At the core of a black hole, these strings could tangle into a dense, complex structure called a fuzzball, completely eliminating the singularity and its destructive infinities. In this view, there is no sharp boundary at the event horizon, only a gradual transition into this tangled quantum knot. Loop quantum gravity, on the other hand, suggests that space-time itself is woven from a network of finite loops. This fabric cannot be compressed into an infinite point, meaning the singularity is replaced by a quantum bounce. The matter collapsing into a black hole would be squeezed to an extreme density, but then rebound, potentially exploding out into a new region of space-time, perhaps even creating a new universe. These ideas lead directly to one of the most heated debates in modern physics, the information paradox. Quantum mechanics states that information about a physical system can never be truly destroyed. If you burn a book, in theory, you could recover its information from the smoke and ashes. But what happens when you throw a book into a black hole? According to Einstein's relativity, the book's information would be irretrievably lost behind the event horizon, eventually vanishing when the black hole evaporates through Hawking radiation. This creates a fundamental contradiction. To resolve this, some physicists propose the shocking firewall hypothesis. It suggests that the event horizon is not a gentle threshold, but a blistering wall of high-energy particles that would instantly incinerate anything falling in. This preserves information but violates the principle that falling through the horizon should be an uneventful process. The debate rages on, with newer ideas like holographic duality suggesting that all the information about what falls into a black hole is not lost inside, but is somehow encoded on its two-dimensional surface, like a cosmic hologram. The true nature of the black hole's heart remains one of the ultimate mysteries. a place where the universe hides its deepest secrets about the connection between information, gravity, and the very nature of reality. Far beneath the Antarctic ice lies a telescope that sees with a ghostly vision. It is not built to capture light, but to hunt for phantoms, particles that can pass through entire planets as if they were not even there. These are neutrinos, and the most energetic of them carry secrets from the most violent frontiers of the cosmos. The Ice Cube Neutrino Observatory is an incredible feat of engineering, a detector made of a cubic kilometer of the purest, deepest Antarctic ice. Embedded within this frozen expanse are over 5,000 sensitive light sensors, waiting for the telltale flash of a rare event. The moment a single, ultra-high-energy neutrino smashes into an atom in the ice. When this collision happens, it creates a secondary particle that briefly travels faster than light can move through the dense ice, producing a faint blue shockwave of light known as Cherenkov radiation. This faint, ethereal glow is the only signature of a ghost that may have traveled billions of light years to die here. The energies involved are almost incomprehensible. These are not the low-energy neutrinos constantly streaming from our sun. An ultra-high-energy neutrino can carry millions of times more energy than the most powerful protons we can smash together in the Large Hadron Collider. They are cosmic bullets fired from nature's ultimate particle accelerators. Identifying the source of these ghostly bullets is a monumental challenge, but on September 22, 2017, IceCube scored a historic victory. It detected a single high-energy neutrino and was able to trace its path back to a point in the sky. An alert was sent out to observatories around the world, and telescopes swiveled to look. What they found was a blazar, a supermassive black hole at the heart of a distant galaxy, devouring material and firing a jet of radiation and particles directly at Earth. This was a smoking gun, the first time a high-energy neutrino had been convincingly linked to a specific celestial object. It proved that blazars are indeed cosmic particle accelerators, capable of generating not just light, but also these elusive high-energy ghosts. But blazars are not the only suspects. The universe is filled with cataclysms that could produce such particles. A tidal disruption event, for instance, occurs when a star wanders too close to a supermassive black hole and is violently shredded by tidal forces. The resulting carnage, as the star's material is heated and consumed, could easily generate a torrent of high-energy neutrinos. Other potential sources include the chaotic environments around colliding galaxy clusters or the furious winds from pulsars. Each neutrino that IceCube captures is a messenger from one of these cosmic infernos, and its energy and direction are a clue to the engine that created it. What makes these ghostly particles so invaluable is their neutrality. Unlike charged cosmic rays, which are deflected by magnetic fields as they travel, making their true origin impossible to pinpoint, neutrinos fly in a perfectly straight line. They do not interact with magnetic fields or dust. They simply pass through everything. This means that when a high-energy neutrino arrives at Earth, it points directly back to its source, offering a clean, unambiguous arrow to the most powerful and hidden events in the universe. They allow us to see into the hearts of these violent phenomena in a way that light alone never could. The hunt for these cosmic ghosts is just beginning, and every flash in the deep ice brings us closer to understanding the fundamental engines that shape the most extreme environments in existence. That ghostly cold spot in the cosmic microwave background is far more than a statistical fluke. It is a colossal region of space, nearly 1 billion light-years wide, that is significantly colder than the surrounding afterglow of the Big Bang. For years, the leading explanation for this cosmic chill has been a supervoid, an immense bubble of relative emptiness in the cosmic web. The physics behind this is known as the integrated Sachs-Wolf effect. Picture a photon, a particle of light from the Big Bang, traveling for billions of years to reach us. As it flies through the universe, it must climb in and out of the gravitational wells created by dense clusters of matter and dark matter. Normally, as it climbs out of a well, it loses energy and its wavelength stretches, becoming redder. But if the universe is expanding at an accelerating rate due to dark energy, something strange happens. The gravitational well itself can become shallower while the photon is still inside it. The photon does not have to work as hard to escape, so it loses less energy than it should. If that photon then passes through a vast void, a region with less gravitational pull, it actually gains a tiny amount of energy, making it appear slightly hotter. Conversely, a photon entering a void and then exiting into an average density region will lose a bit more energy and appear colder. This is precisely what could be happening on a gargantuan scale with the cold spot. The light from the CMB passing through a proposed Eridanus supervoid would lose extra energy, creating the cold imprint we see on our maps. Yet, the plot thickens when astronomers try to find this supervoid. Detailed galaxy surveys do show a underdense region in front of the cold spot, but it is not nearly as vast or as empty as the theory requires to fully explain the temperature drop. The observed void is a significant cosmic desert, but it seems too small to account for the profound cold. This mismatch has opened the door to far more exotic possibilities, ideas that stretch the very definition of reality. The most breathtaking theory is that the cold spot is a bruise, a cosmic scar from a collision with another universe. In the multiverse scenario, our universe is just one expanding bubble in a frothing sea of countless other bubble universes. If another bubble universe with fundamentally different physical laws bumped into our own in the distant past, the energy exchange at the boundary could have left a distinct circular imprint on the cosmic microwave background. This collision would have drained energy from that region of space, creating a spot that appears anomalously cold. The precise properties of the cold spot, its size and its sharp edges, make it a compelling, if speculative, candidate for such an event. The evidence remains circumstantial, a tantalizing hint written in the oldest light. Proving a multiverse collision is, by its very nature, an immense challenge. The cold spot, therefore, stands as a monument to our ignorance. It is a cosmic Rorschach test where we see either a rare but natural structure in the cosmic web, or the first tangible evidence that our universe is not alone. Its enduring mystery pushes cosmology to its limits, forcing us to ask if the most profound discoveries lie not in the bright lights of the cosmos, but in its faintest, coldest shadows. These magnetic fields are not gentle forces. They are immense cosmic structures woven through the disks of spiral galaxies. They stretch for tens of thousands of light years, guiding the flow of cosmic rays and influencing how stars are born. Yet their very existence is a puzzle. How can such vast, organized magnetic fields persist across the entire span of a galaxy? The leading answer lies deep within the churning, turbulent gas between the stars, a process known as the galactic dynamo. Picture a galaxy as a colossal spinning engine. Its rotation provides one crucial ingredient. The second is turbulence, the constant chaotic motion stirred up by supernova explosions and stellar winds. This combination acts like a self-sustaining power generator. It takes the weak, random magnetic fields that might already exist and amplifies them, stretching and twisting the magnetic field lines into a coherent, large-scale structure. It is a feedback loop of cosmic proportions, where motion creates magnetism, and that magnetism in turn influences the motion. The dynamo theory is elegant, but it demands a seed. Every dynamo needs a small magnetic field to get started, a spark to amplify. Where did these initial seeds come place in the early universe? This is one of the deepest parts of the mystery. One possibility is that they were generated in the violent aftermath of the Big Bang itself. During the period of cosmic inflation, when the universe expanded faster than light, immense pressures and temperatures could have created fundamental electromagnetic fluctuations, planting the first faint magnetic seeds throughout the cosmos. Another idea points to the first generation of stars and galaxies. Their powerful radiation and colossal supernova explosions could have flooded space with currents of charged particles, generating local magnetic fields that were later swept up and amplified as galaxies form. The challenge is that these primordial fields would have been incredibly weak, and explaining how they survived to be amplified is a major focus of research. To visualize these fields, imagine a spiral galaxy not just as a collection of stars, but as a complex machine threaded with invisible lines of force. These magnetic lines are not straight. They are frozen into the galaxy's ionized gas and are stretched by its rotation into a grand spiral pattern, often following the glowing arms of stars. They are invisible to our eyes, but astronomers can map them by studying the polarization of starlight or the radio emissions from cosmic rays spiraling along these magnetic highways. The strength of a galactic magnetic field is minuscule compared to Earth's, but its scale is what boggles the mind. Maintaining coherence over such vast distances, despite the chaotic turbulence, is a delicate balancing act. Without this invisible architecture, our galaxy would be a very different place, and the story of how it came to be is still being written in the forces we cannot see. Our cosmic inventory holds a stubborn mismatch that reaches back to the very first minutes of creation. In the hot, dense furnace of the Big Bang, nuclear fusion forged the universe's first light elements, a process called Big Bang nucleosynthesis. The theoretical calculations for this process are incredibly precise, successfully predicting the observed cosmic abundances of hydrogen and helium with stunning accuracy. Yet, for the third lightest element, lithium, the numbers fail spectacularly. The oldest stars in our galaxy, which should preserve the pristine chemical composition of the early cosmos, contain only about 1/3 of the lithium that our models insist should be there. This is the cosmological lithium problem, a quiet but profound error in the account of our origins. So where did all the lithium go? One possibility is that our understanding of nuclear physics in that primordial inferno is incomplete. The predicted amount of lithium-7, the main isotope produced, depends on the precise rates of a chain of nuclear reactions. Perhaps a previously unknown reaction pathway or a slight miscalculation in a key reaction rate could have destroyed lithium as quickly as it formed. Scientists have probed these nuclear cross-sections in laboratories, but the extreme conditions of the infant universe are difficult to replicate, leaving room for hidden errors. Another compelling line of thought points to the stars themselves. Could these ancient stellar furnaces be slowly destroying the lithium over billions of years? As a star churns and rotates, lithium in its outer layers can be dragged down into the hotter interior, where temperatures are high enough to burn and destroy it. Certain types of stellar vibrations or deep magnetic mixing could act as a cosmic blender, permanently removing this fragile element from view. If this depletion is efficient and universal, it could resolve the discrepancy, but proving this mechanism works across all ancient stars is a complex challenge. The most radical solution, however, ventures beyond known physics. Could the lithium problem be a hint of something entirely new at play in the universe's first moments? Some theorists suggest that exotic particles, like certain types of dark matter, were present during nucleosynthesis. These particles could have interacted with the primordial nuclear soup, altering reaction rates and effectively suppressing lithium production. Others have considered whether the fundamental constants of nature, like the strength of the gravitational force, were slightly different back then, a change that would have thrown off the delicate nuclear balance. A chart comparing predicted and observed abundances would show a near-perfect alignment for hydrogen and helium, but a glaring, empty gap where lithium should be, a silent testament to a mystery that has endured for decades. This missing lithium is not a minor accounting error. It is a clue etched into the atmospheres of the most ancient stars we can find, a whisper from the dawn of time that our story of creation is not yet complete. The fate of the cosmos hinges on a single, invisible force we do not understand. Dark energy, the phantom driver of cosmic acceleration, holds the key to our ultimate destiny, and the possibilities are as profound as they are unsettling. One of the most discussed endpoints is the Big Freeze, also known as heat death. In this scenario, dark energy remains constant, and the universe continues expanding at an ever-increasing rate. Billions of years from now, the last stars will flicker out, their fuel exhausted. Galaxies will drift so far apart that their light can no longer cross the growing void. The universe will become a cold, dark, and increasingly empty place, filled only with the decaying embers of black holes and isolated subatomic particles, a silent and final state of maximum entropy where all activity ceases. A far more violent end is the Big Rip. This occurs if dark energy is not constant, but instead grows stronger over time, its repulsive force becoming dominant over all other forces in the universe. First, the accelerating expansion would tear apart galaxy clusters, then individual galaxies. As the end draws near, stars would be ripped from their systems. In the final, terrifying moments, the repulsive force would overcome the gravity holding planets together, then the electromagnetic forces binding atoms, and finally the nuclear forces within atomic nuclei. The very fabric of space-time itself would be shredded, ending the universe in a catastrophic, instantaneous dissolution of all structure. A third, classic possibility is the Big Crunch, a dramatic reversal of our current expansion. This would require dark energy to weaken or reverse, allowing the collective gravity of all matter and dark matter to finally halt and reverse the universe's growth. The cosmos would begin collapsing in on itself, a mirror image of the Big Bang. Galaxies would rush together, and the background temperature of space would rise. Eventually, everything would be compressed into an ultra-hot, ultra-dense state, potentially triggering a new Big Bang and a cyclical universe. This poetic idea of a phoenix cosmos, however, is currently out of favor, as observations strongly suggest the acceleration is here to stay. The deciding factor between these fates is not just the strength of dark energy, but the ultimate shape and density of the universe. If the cosmic density is just right, space will be flat and expand forever. A lower density could lead to an open, saddle-shaped universe that also expands indefinitely, while a higher density would result in a closed, spherical universe that eventually collapses. Our best measurements indicate a flat or nearly flat universe, pointing toward an eternal expansion and making the Big Freeze the most likely outcome based on current data. Yet, the true nature of dark energy remains the wild card. Future observatories like the Vera C, Rubin Observatory, and the Nancy Grace Roman Space Telescope will map the expansion history with unprecedented precision, watching for any subtle changes in dark energy's behavior over billions of years. The ultimate fate of all existence is written in the invisible push of this mysterious energy, and we are only just beginning to read the first few words. At its deepest level, the smooth, continuous space-time described by Einstein may be an illusion. The conflict between the cosmic scale of general relativity and the subatomic world of quantum mechanics represents the greatest unsolved problem in physics. Einstein's theory paints gravity as the elegant warping of a smooth space-time fabric, while quantum mechanics reveals a probabilistic, jittery world of discrete particles. These two pillars of modern physics are fundamentally incompatible, and their clash becomes catastrophic in extreme environments like the center of a black hole or the first moment of the Big Bang, where both theories must apply. To resolve this, physicists are searching for a theory of quantum gravity, a framework that would describe the force of gravity according to the rules of the quantum world. One of the most mind-bending concepts in this search is space-time foam. This idea suggests that if you could peer down to the tiniest possible scale, the Planck length, the fabric of the cosmos would not be smooth and tranquil. Instead, it would be a chaotic, boiling froth. Tiny wormholes and baby universes would constantly blink in and out of existence, a seething ocean of quantum turbulence where the very concepts of here and there, before and after, lose all meaning. Another revolutionary idea is the holographic principle. It proposes that all the information needed to describe a volume of space can be encoded on its boundary, just as a three-dimensional image is stored on a two-dimensional holographic film. In this view, our perception of a three-dimensional universe might be a projection from information stored on a distant, two-dimensional surface. This would mean that reality, at its most fundamental level, is a kind of cosmic illusion, and the richness of our world is a holographic projection. This leads to the profound possibility that space and time are not fundamental. Perhaps they are emergent properties, collective behaviors that arise from something deeper and more abstract. Think of the way temperature emerges from the frantic motion of countless molecules. No single molecule is hot or cold, but their collective motion creates the property we call temperature. In the same way, the smooth continuity of space and the steady flow of time might emerge from a vast network of discrete, interconnected quantum bits. Visualizing this is a challenge, as it exists far beyond human experience. Imagine the universe not as a stage upon which events unfold, but as the events themselves, woven together in a vast dynamic web. Each intersection in this web could be a discrete unit of space-time, a pixel of reality, vibrating and interacting with its neighbors to create the seamless cosmos we perceive. The quest for quantum gravity is a journey to the ultimate foundation of reality, where our everyday understanding of space and time simply dissolves into a deeper, more mysterious quantum architecture. Gravity is the ghost at the cosmic feast. It sculpts galaxies and guides planets, yet on the smallest scales, it is almost laughably weak. A simple refrigerator magnet can generate enough electromagnetic force to defy the gravitational pull of our entire planet. This bizarre mismatch is known as the hierarchy problem, and it asks a deeply unsettling question. Why is gravity so many orders of magnitude weaker than the electromagnetic force, the strong nuclear force that binds atoms, and the weak nuclear force behind radioactive decay? This is not a small discrepancy. The difference in strength is a factor of 1 followed by 34 zeros, a number so vast it defies any simple explanation. It suggests our understanding of gravity is fundamentally incomplete, that we are missing a crucial piece of the puzzle that connects the cosmic realm to the quantum world. One of the most mind-bending proposals is that gravity is not inherently weak, but only appears that way to us. This idea, stemming from string theory, posits the existence of large extra dimensions of space beyond the 3 we experience. In our familiar world, the 3 fundamental forces are confined to our 4-dimensional space-time, like waves traveling on the 2-dimensional surface of a pond. Gravity, however, could be different. It might be the only force that can leak out, spreading its influence into these extra, compact dimensions. From our perspective, this dilution would make gravity seem incredibly feeble. Imagine a powerful sound wave spreading out in a vast, empty hall. To a listener in one small corner, the sound would be faint and weak. That could be our experience with gravity, only feeling a tiny fraction of its true strength as it dissipates into a higher dimensional reality. Another elegant solution is supersymmetry, a theoretical framework that proposes every known particle has a hidden, super-heavy partner. This symmetry would provide a natural cancellation effect, stabilizing the mass of the Higgs boson and, by extension, the scale of the weak force. If supersymmetry is real, it would neatly resolve the hierarchy problem by introducing a beautiful mathematical balance to the particle zoo. The heavier partners of photons, electrons, and quarks would have interacted in the early universe to precisely cancel out the extreme effects that make gravity seem so weak by comparison. This would explain why the scales of nature are so vastly different. Yet, for all its mathematical beauty, we have found no direct evidence for these superpartners, despite extensive searches at the Large Hadron Collider. A more philosophical answer is the anthropic principle. This line of reasoning suggests that the fundamental constants of nature, including the strength of gravity, are not predetermined by any grand theory. Instead, they are what they are because if they were even slightly different, we would not be here to observe them. In a universe where gravity was only slightly stronger, stars would burn through their fuel too quickly for life to evolve. If the other forces were weaker, complex atoms could never form. Our existence, therefore, depends on this precise and seemingly unnatural tuning. We find ourselves in a cosmic oasis where the numbers just happen to allow for galaxies, stars, planets, and life. This is not so much an explanation as a recognition of our own place in the cosmic lottery. How do we test these extraordinary ideas? The Large Hadron Collider continues its hunt, smashing protons together at nearly the speed of light, hoping to create a supersymmetric particle or even detect a microscopic black hole. The creation of a tiny black hole would be a smoking gun for large extra dimensions, as it would prove that gravity becomes strong at energies far lower than we thought, within the compactified higher dimensions. Meanwhile, gravitational wave observatories like LIGO and Virgo are listening to the ripples in space-time from colliding black holes. The precise properties of these waves, their frequencies, and how they ring down could carry subtle imprints of extra dimensions, warping the signal in ways that would reveal the hidden architecture of the cosmos. The solution to this profound weakness may be waiting in the data, a whisper from a reality far stranger than we ever imagined. This exponential expansion solves some of the most profound puzzles about the cosmos we see today. Why does the universe appear so flat and uniform in every direction, as if every part was once in intimate contact? The answer lies in a concept called cosmic inflation, a period of unimaginably rapid growth that occurred a tiny fraction of a second after the universe began. During this epoch, the cosmos ballooned from smaller than a proton to a size larger than our entire observable universe, all in less than a billionth of a billionth of a billionth of a second. This violent stretching ironed out any initial wrinkles, smoothing the universe into the flat, homogeneous expanse we observe, while also planting the seeds for all future structure. The most compelling evidence for this incredible event is written in the cosmic microwave background. The slight temperature variations in this ancient light, those hot and cold spots, are the direct descendants of the quantum fluctuations that were magnified to cosmic proportions during inflation. These microscopic ripples became the gravitational blueprints for galaxies, clusters, and the entire cosmic web. Without this initial push, the universe might have collapsed back on itself or flown apart into a featureless void, never giving rise to the complex structures we see. The engine behind this fantastic growth is a hypothetical field known as the inflaton. Think of it as an invisible energy field that temporarily possessed a peculiar property, a kind of negative pressure that caused gravity to become repulsive. This repulsive gravity drove the exponential expansion, stretching space itself faster than the speed of light. But just as mysteriously as it began, inflation had to end. The inflaton field eventually decayed, like a ball finally rolling down a hill, releasing its pent-up energy in a fiery burst that repopulated the universe with particles and radiation, effectively starting the conventional hot Big Bang. The end of inflation was the true beginning of the universe as we know it. Yet, for a theory that explains so much, cosmic inflation is shrouded in its own deep mysteries. We have no idea what the inflaton field actually is. Is it a fundamental particle, a cousin to the Higgs boson, or something entirely beyond our current physics? We do not know what triggered this explosive phase, or why it lasted for the precise duration that gave us our specific universe. Even more mind-bending is the concept of eternal inflation, which suggests that once started, inflation never truly stops everywhere. Our entire observable cosmos might be just one bubble in a vast, ever-expanding multiverse, a single island of stability in an infinite, frothing sea of inflating space, where different regions have different physical laws. This leaves us with a humbling thought. The majestic universe we study, with all its galaxies and voids, might be the product of a quantum hiccup in a field we cannot see, a fleeting event from the first moment of time whose true nature remains one of the greatest enigmas of all. This grand cosmic narrative, from its smooth beginning to its mysterious end, might not be a singular story at all. The final, and perhaps most profound, mystery is the possibility that our entire universe is just one bubble in an infinite cosmic foam, a single page in a library of realities known as the multiverse. This is not a single idea, but a collection of theories that all point beyond the horizon of our own cosmos. One compelling version arises from the theory of cosmic inflation. If inflation can start, it may never truly stop, becoming eternal. In this scenario, the rapid expansion of space continues forever in a background meta-universe, while in localized pockets, inflation ends, each one birthing a separate bubble universe with its own Big Bang. Our entire observable cosmos is just one such bubble, and beyond its impenetrable horizon, an infinite number of other bubbles float in the inflating void, each potentially with different fundamental constants and physical laws. A completely different kind of multiverse emerges from the strange world of quantum mechanics. The many worlds interpretation suggests that every time a quantum event has multiple possible outcomes, the entire universe splits to accommodate each one. In this view, a cosmic tree of forking paths exists, with every choice, every random particle decay, creating a new, equally real branch of reality. There is a version of history where the dinosaurs never went extinct, and a version where you made a different decision this morning, with all these timelines unfolding simultaneously in a vast, branching continuum. String theory adds another layer with its landscape of possible vacuums. The theory allows for a staggering number of possible stable configurations for the extra dimensions it proposes, perhaps as many as 10 to the 500. Each configuration corresponds to a universe with a different set of physical constants and laws. In this landscape, our universe is simply one fortunate valley where the numbers allowed for galaxies, stars, and life to form, a rare oasis in a desert of lifeless possibilities. The philosophical implications are staggering. If an infinite number of universes exist, then everything that can happen does happen somewhere. The precise tuning of our universe's constants, which seems so miraculous, becomes a simple selection effect. We find ourselves in a universe capable of supporting life because we could not exist in the overwhelming majority that are sterile. This anthropic reasoning offers an explanation for our lucky cosmic lottery ticket, but it also challenges our sense of uniqueness. The ultimate question is whether this is science or mere philosophy. Can we ever test for the existence of other universes? Some scientists propose looking for bruises. If our bubble universe collided with another in the distant past, the energy of that impact could have left a distinct, circular imprint on the cosmic microwave background, a cold spot or a strange pattern of polarization that defies any other explanation. Others suggest that the elusive nature of dark energy or the specific properties of gravitational waves might carry fingerprints from these larger cosmic structures. For now, the multiverse remains a breathtaking speculation, a horizon of thought that redefines reality itself. It suggests that all the mysteries we have explored, from dark matter to cosmic voids, might be local bylaws in our particular bubble, and that the true nature of existence is vaster and more wondrous than we can possibly conceive. From the ghostly pull of the Great Attractor to the silent, profound question of the Fermi Paradox, these 25 cosmic mysteries are more than just puzzles. They are the boundaries of our current understanding, the edges of the map where our knowledge fades into wonder. Each one, from the nature of dark matter to the true fate of the universe, reveals a fundamental gap in our story of reality. They remind us that our most cherished theories are provisional, always awaiting the next discovery that could shatter them and reveal a deeper truth. This is the thrilling frontier of astronomy and physics, a perpetual journey into the unknown where every answered question unveils two more. We want to hear which of these cosmic enigmas captures your imagination the most. Does the chilling silence of the universe haunt you, or does the bizarre nature of dark energy fire your curiosity? Share your thoughts in the comments below, and let us know which mystery you believe we should solve first. If exploring the deepest questions of the cosmos excites you, be sure to subscribe for more journeys to the edge of understanding. Our drive to look up and ask why, to send probes into the void and telescopes to the edge of time, is what propels us forward. These mysteries are not walls, but invitations, calling us to keep exploring, to keep questioning, and to continue our timeless search for meaning in the vast, star-filled dark.